Hi, my name is Tony Shaska from Oakland University in Rochester, Michigan, and I will talk about something rather interesting today about the addition on Jacobian varieties. And so in order to do that, we will just try to take a very geometrical approach. So let's see. We'll just start with low genus curves. So I'll give a brief review of the conics and elliptic curves, and then we'll just go to genus 2 curves and then hyperelliptic curves. We'll describe geometrically how the Jacobian works in such curves. I mean, how the addition works in such Jacobians. And then we'll see if we can just generalize this a little bit more. And so in order to do that, we'll have to go over Max Noethern's fundamental theorem, Noethern gap theorem, and then see if we can generalize such techniques to superelliptic curves. So let's just see from the very beginning. So I have a conic, so conic C, and this has a rational point if and only if its discriminant is a square in field K. So we assume that there is a rational point in our conic, okay? Then we fix this rational point. This will be our group identity. And for any 2 points P and Q on the conic, I draw a parallel line parallel to the identity and call this line PQ. This line will intersect the conic in another point, okay, R, and and this point R will be P plus Q. So this is a abelian group. All of these things are rather easy to prove, and one nice reference here to see some of these things is this book of Silverman and Tate on the rational points on elliptic curves, the undergraduate version of the Silverman's book. Okay, so how does that work? So if you give me a conic in general, for any 2 points with coordinates, so P and Q, with coordinates as given here, alpha 1, beta 1, and alpha 2, beta 2, the formula for the conic, when you take the point, the 0, take the point 0, 0, so the origin of the group will take it the origin, will be basically given this way, where this lambda is basically the slope of the line PQ. Okay? And this lambda takes a different value if P are equal to Q. So that is actually then in that case the tangent. So let's just say this N, for example, is the origin now, and I have P and Q. So from N I draw the parallel line, and this is PQ, right? And if N is the origin, and now I want to add P plus P, then I take P and I draw the tangent now at that point, and that will be basically, P plus, I'm sorry, so I draw the tangent at that point, and then from N draw the line parallel to the tangent, right, and I will get P plus P. Okay, so this was kind of easy. So what happens for elliptic curves? Well, this is part of the math folklore. I mean, we all know this. Every elliptic curve can be written, as long as the characteristic of the field is not equal to 2, can be written in its Weierstrass form this way, where this f of x is degree 3 or 4. Let's just take the easiest case. We assume that infinity is one of the branch points of the hyperelliptic projection, so I can take 0, I mean the origin of the group, to be infinity, and in that case this will be a degree 3 polynomial. This is a picture when that degree 3 polynomial has 3 rational roots, I mean 3 real roots, I'm sorry, but it doesn't have to be, I mean that's not a restriction. So if you take now P and Q, any 2 points, you just add, I mean you just draw the line between 2 points. From the so-called Bezout's theorem, we'll talk more about this, a line always intersects the elliptic curve or a cubic curve in 3 points if you count these points of intersection the right way, okay? And so this is a third point. You take now the vertical line, so you take the symmetrical of this with respect to the x-axis, which is somewhere here, yes, and you'll get this p plus q. So that will be now the addition defined on an elliptic curve. So can we do this in general? Well, we have to be a little bit careful now. So let's just say we go to a genus 2 curve. So a genus 2 curve is given this way. And again, we are assuming the characteristic is not 2 and 3. So it's given this way. So y squared, so they are all hyperelliptic, genus 2. So y squared is equal to f of x this way. And again, we are actually taking infinity to be one of the Weierstrass points. So this is degree 5. Okay, but this curve cannot be made into a group, so this we know. But it can be embedded into what we call it the Jacobian of the curve, so it can be embedded into an abelian group. That's what the Jacobian is. So what is really the Jacobian? So you take C cross C, okay, so the Cartesian product of the curve by itself, and then you actually have some linear equivalence, some equivalence relation defined there, and the Jacobian is actually the quotient map of that equivalence. I'll say more about this later. But so what does that mean? So points here in the Jacobian are ordered pairs of points here. Well, the equivalences of these ordered pairs. Okay, we call these elements in the Jacobian, we call them divisors. So the problem now becomes I have two divisors, d1 and d2 in the Jacobian. Okay, both are given, have some representative of an ordered pair of points on the curve, and I want to learn how to add them. So what does that mean? Well, it means that I have to find out now, given these 4 points which determine these two divisors, I have to find this new divisor, d1 plus d2, which will correspond to another pair of points, let's just say p5 and p6, right? So how do we do it? We determine a curve given by this equation, going through these points p1, p2, p3, and p4. Here, for some reason, I'm calling it p1, p2, q1, q2. Okay, but basically these 4 points, and you will see that there is a unique curve which actually will do this job. So there is a unique. I should put here another b0 coefficient here, but there is an exactly unique curve which interpolates these 4 points in a cubic curve. Okay, and so this is, and so this curve will intersect the initial curve, the original curve C, into exactly 6 points. Now that's kind of easy to see, because if you take this cubic and you plug it in here, you'll get a 6-degree polynomial on the left and 5 from the right. You have to solve this equation in x, which is degree 6. You'll get 6 points. 4 of them are the coordinates of the 4 given ones, so you have 2 new points, and these are the coordinates of the pair now p5 and p6, which will determine our divisor. Almost it will determine that divisor. Okay, so let's see how it works. So p1, p2, p3, p4, you will get now this, right, this interpolating curve. It will intersect this in p5 and p6. This is not the addition. What it is, the addition is you have to take now the symmetrical points with respect to the x-axis of this p5 and p6, so p5 prime and p6 prime. And what we know is that d1 plus d2 will be determined now by this p5 prime and p6 prime. And this basically is how it works in genus 2. And let's see if we want to find out if this works for higher genus. And so the answer is yes. And It is basically mathematically or computationally what is known as Cantor's algorithm, which was sometime in 1987 for elliptic curves, so for hyperelliptic curves or hyperelliptic Jacobians. And you can find a description, a brief description of this algorithm on my paper with Fry from last year. So how does that work? In this case, if you have a genus G hyperelliptic curve, you have D1, a G tuple of points, a divisor, and D2 another one. So you are given 2 G points altogether. Well, you actually interpolate these things with a curve. And the curve you want to use for this interpolation is basically a rational function. So your curve will be y is equal to b of x over c of x, where these are actually polynomials. So you want the smallest degree rational function that will interpolate these 2g points. And well, that gives you a curve, namely this curve here, that will intersect the original curve in precisely g points. We call them p. We call them p2g plus 1 to 3g, right? So now these points, these are the new g points. And you do the same trick. For this now new g point, you take the symmetrical of that with respect to the x-axis, and you get another set of g points. Here I'm calling them 3g plus 1 to 4g. But basically, this new set of g points is determining the addition divisor, so the sum of d1 and d2. So here is what we want to do. We just want to do the following. Can we extend this geometrical method to the group law in general? And let's just remind ourselves what we have. Well, a divisor in the Jacobian of C is still, so this is true, is still determined by a G tuple of points. Okay? Now we need to find a way how to compute or how to determine or how to define this interpolating curve, this C prime. So we need a curve that intersects the original curve in precisely 3g points, because I would be given 2g points because I have two divisors, so we need to do this in 3g points. And once we do that, now I will have now a g tuple of points. Okay, now that's not going to be the addition. However, we want to find a way to substitute or to replace these taking symmetric points with respect to the x-axis. Obviously, that had something to do with dealing with hyperelliptic curves, which are symmetric with respect to the x-axis. There is no such thing in general for general curves. So how would you do that? Well, we will just basically see if we can extend that to